Okay, so the plan for today is to work through section 4.7, graphing systems of linear inequalities. That'll finish up chapter 4 on linear systems. Note that we skipped 4.5 and 4.6, solving linear systems with matrices and determinants, things like that. I mentioned before, I don't think that that's really a topic that is best covered in this course. It's a very useful topic, but just the background needed to actually understand it properly is just beyond the scope of this course. So we might be able to functionally plug some things in the calculator and get answers out, but I think understanding what's actually going on behind the scenes is not really accessible at this level. So after 4.7, we're going to move into chapter 5, starting into our discussion of polynomials and polynomial functions, and starting with adding and subtracting polynomials. So that's the plan for today. Note that the graphing utility on WebAssign can be a little bit troublesome to use sometimes. Troublesome is not the right word. Maybe it has a little bit of a learning curve. It's a little bit unintuitive to use sometimes. So there are two supplements on Blackboard in the supplemental materials folder. One is kind of on basic graphing, and one relates more to this graphing systems of linear inequalities that we're talking about today. So if you're having any trouble using that utility, check out that supplement on Blackboard, that PDF, and that should walk you through it. And of course, as always, if you have any questions after looking over that, you can always shoot me an email or pop into office hours, anything like that. Okay, the quote of the day for today is, "One physical test is worth 1,000 expert opinions." In many of our, what we might call hard sciences, things like physics and chemistry and so on, roughly speaking, it doesn't matter how important the person is that's making some claim, or how elegant their proof is, or how elegant their model is. If it disagrees with experiment fundamentally, then it's wrong. So that's something to kind of keep in mind about the sciences is, at the end of the day, the arbiter of truth in the sciences is the experiment. Does the model agree with the real world or not? And of course, there are caveats to that. Like, does it agree? No model is going to agree perfectly with the real world, but Newtonian mechanics agrees nicely enough with the real world in a lot of circumstances that it's a very useful model. So um, does it agree to the extent that that we're able to test in an experiment, or to the extent that we care about, or is the trade-off between a little bit less accuracy but a lot more simplicity? Is that a good trade-off? So there's a lot of caveats to this kind of idea, but the point is that in the hard sciences, physics, chemistry, even sciences like biology or even economics to some extent, if somebody has a really nice opinion or theory, doesn't matter who they are, if it doesn't work in practice, it's not really seen to be correct. This is as opposed to math, where uh, we make no claim about the real world in math. We say we have this logical structure, we have axioms, assumptions that we make, we build upon those with logic, we build theorems, we build conclusions, and the structure is in and of itself. Now, do we build structures that we intend to be used to solve particular real world problems? Well, sure. But the structure is really its own thing, separate from reality. So you can't, say, well, 1 + 1 = 2 is wrong because binary arithmetic or something like that. And it's like, well, I mean, that's just maybe a poor application of that model. So this kind of goes back to a previous quote from the statistician George Box, that all models are wrong, but some models are useful. Okay, so that was the thought for today. So moving on to 4.7, graphing systems of linear inequalities. So here we have a linear system. We have a system, multiple mathematical claims. I really want to say equations, but these are not equations. These are multiple mathematical claims, two of them in this case, in two variables. And they're coupled together. And each of these claims could independently be true or false. If I had two equal signs here, 3x plus y equals 5 and 2x minus y equals 10, I would have a certain kind of mathematical claim. I would be looking for probably most of the time, one ordered pair, x comma y, that makes both of those equations true at the same time. Well, what changes here? Well, not much conceptually changes. I have two inequalities in this case, two mathematical claims still, slightly different form of mathematical claim than an equation, an inequality. And I'm looking for one or more ordered pairs, x comma y, that simultaneously make the two statements true. Now, with an inequality, we might have a gut feeling that for a system of inequalities, for a system of equations, we basically would either have one solution, one point that represents a solution, which was kind of the typical thing that we were looking for, or we might have an edge case where we have infinitely many solutions or zero solutions. So we had kind of 0, 1, or infinity as our number of solutions. We might kind of guess that with inequalities, we're maybe going to often get a lot of solutions. If I find a point that satisfies both of these inequalities at the same time, I probably can get away with wiggling that point just a little bit and come up with another point that also satisfies the inequalities at the same time, right? Okay, so let's check each of these 4 different points and just see whether they're solutions to this system of inequalities. Probably actually will need a little more room than I gave myself here. Okay, so for 3 comma negative 3, is it true that 3x or 3 times 3 plus y or plus negative 3 is bigger than 5? So is that true? We have 9 minus 3 is 6, bigger than 5. That is true. This satisfies the first inequality. And check the second. 2 times x or 2 times 3 minus y or minus a negative 3. Is that less than or equal to 10? Well, that is what? 6 plus 3 is 9. Is that less than or equal to 10? Yes, it is. 9 is less than or equal to 10. 3 comma negative 3 is a solution to this system. What about 7 comma 1? We'll check the first inequality. Is it true that 3 times 7 plus 1 is bigger than 5? 21 plus 1 is 22, bigger than 5? Yes, it is. And is it true that 2 times 7 minus 1 less than or equal to 10? Well, wait, we have 14 minus 1 is 13. Is 13 less than or equal to 10? No, it's not. My second inequality is not satisfied. This does not represent a solution to the system of linear inequalities. And we check these last two as well. X equals 5, y equals 0. Is it true that 3 times 5 plus 0 is bigger than 5? Yes, it is. Is it true that 2 times 5 minus 0 is less than or equal to 10? Well, that's 10 less than or equal to 10. That is true. It's right on the edge of that second inequality, but it does satisfy it just barely. And is 1 comma 2 a solution? Is it true that 3 times 1 plus 2 is strictly bigger than 5? Is it true that 5 is strictly bigger than 5? No. Just barely lies outside of that first inequality. Since it doesn't satisfy the first inequality, we don't even have to check the second. So we know that 1 comma 2 is not a solution. It doesn't satisfy the first inequality. So we're done. We know it's not a solution to the system. But we do see that in this case, we have at least 2 points that satisfy the system. This isn't one of those like strange edge cases where one of them is just like a multiple of the other, where we just have two parallel lines. So what's really going on here? Well, let's graph these. Let's graph these on a two-dimensional plot. So here I have x comma y. Why are my axes so wonky? That looks a little better. And let's start with 3x plus y is bigger than 5, which I can rewrite as y bigger than negative 3x plus 5. So this line y equals negative 3x plus 5 would go through 0, comma 5. And say 1, comma 2. And so if I had the line y equals negative 3x plus 5, it would look like that. So this is y equals negative 3x. I keep wanting to leave off that negative plus 5. Now we're going to come back and we're going to kind of adjust some of this in a bit, but we're just getting the basic idea written out now. If I look at the second inequality, I can kind of think of it as an equation. This would be what? Y bigger than or equal to, so adding the y on both sides, subtracting 10 on both sides, 2x minus 10. So again, if I think of this as an equality, y equals 2x minus 10. So let's see, maybe that's minus 5. This is maybe minus 10. And then y equals 2x minus 10. So if I go over 1, I go up 2. So y equals 2x minus 10. And what I might notice is that these two lines kind of split my 2D plane into 1, 2, 3, 4 sectors. If I come up here and look at these 4 points, I really hope I drew this accurately enough that these points will lie in the right areas. I might have gotten my graph a little bit off, and well, I might have to fix that later. But so if I look at x, note that this is the same system that we just looked at, right? This is the same system as that one. So if I look at these points, 3 comma negative 3, so 3 comma negative 3 looks like it is over here. Yeah, and I do think that let's see. Yeah, my picture is off by a little bit. How much do I have to erase too? Yeah, that's not too bad. Let me adjust my picture here. I might have to adjust it again. This is just from slight inaccuracy of me drawing it. So this is 3 comma negative 3. And this was a solution. 7 comma 1. So over here at, say, 7 comma 1, we extend this line out a little bit. That was not a solution. It did satisfy the first inequality, this black line here, but not the second. If we look at 5 comma 0, that was a solution. Maybe that is like here. A little bit closer. There we go. And if we look at 1, comma 2, that was not a solution. That's this point here. So what I might realize is my solutions are going to be points that fall into probably like one of these four kind of quadrants. We've kind of split the 2D plane into something like four quadrants, but there are like different quadrants than our standard quadrants. In what quadrant am I looking for a solution? Well, I don't actually have an equation here. I have an inequality. I'm looking for XY pairs from the green equation's perspective that satisfy y is bigger than or equal to 2x minus 10. From the green line's perspective, I'm looking for points that are above the green line. From the black line's perspective, I'm looking for XY pairs that satisfy y bigger than negative 3x plus 5. I'm looking for points where the y coordinate is above the black line. So I see, for instance, in what I'm calling kind of quadrant 4 down here, we're above the black line, but we're not above the green line. Nothing in this lower right quadrant is going to be a solution. If I look in quadrant that I kind of labeled 3, well, here we're below the black and the green lines. Those aren't going to be solutions. If I look at the quadrant that I labeled 2 over here, well, we're above the green line, but not above the black line, so we don't satisfy the black inequality. Those are not solutions either. But we do notice that like 5, comma 0 and 3, comma, what was it, negative 3? I think it was 3, negative 3. Those are in this kind of quadrant 1, so to speak. Quadrant 1 is where I'm going to find my solutions. And in fact, any point in here is going to be a solution to this set of linear inequalities. Now, I did notice that I had some edge cases, right? I had 5, comma 0 down here that was right on this green line, which I didn't draw it very well, but should be that it's the x-intercept of that green line, 5, comma 0. And it was a solution. But this point here, what was it, 1, comma 2, is right on the black line, but it was not a solution. So what's happening there? Well, really, what's happening there is that the black inequality relating to the black line is strict. If I fall directly on the black line, not a solution. But the green inequality relating to the green line is non-strict. If I fall right on the green line, I'm still allowed to be a solution, provided that I also satisfy the black inequality as well. Okay, so we've made a pretty good mess out of this picture. Let's erase it, and now that we've got the idea, let's rewrite the solution a little nicer. I'm just going to start from scratch. All right, so here we have y bigger than negative 3x plus 5. And I have y bigger than or equal to 2x minus 10. So we have 5, negative 5, negative 10. We know we go through 5, comma 0. So our green line goes through 0, comma negative 10 and 5, comma 0. So that's my green line. My green line is related to this non-strict inequality. So points that are on the green line are still capable of solving the linear inequality, the system of linear inequalities, provided that the points that are on the green line also satisfy the black inequality. However, the black inequality, it's a strict inequality. The points that lie directly on the black line, y equals negative 3x plus 5, those can never satisfy the system of linear inequalities, because if y equals negative 3x plus 5, it cannot be true that y is strictly greater than negative 3x plus 5. So here I'm going to note my one point on that line, y equals negative 3x plus 5, and I'm going to note it with an open circle. And then what else do I go through? Like 1, comma 2, I'm going to note that also with an open circle. And I want to draw my line through these circles, but I want to indicate that points on this line are not under consideration for solutions for the linear system, because they'll never satisfy that black inequality. The way I denote that is by making this a dashed line. And at this point, I can either kind of use intuition. I know that I have y bigger than or equal to for the green, so I'm looking for solutions that are above the green line, and I'm looking for y bigger than for the black line, so I'm looking for solutions that are above the black line as well. This is, of course, x and y. So I know that my solution region is going to be that kind of upper triangular region. Or what I could do is I could pick a test point in each of the four, pseudo quadrants, and see whether or not it satisfies the system of linear inequalities. And if not, then if a test point in a particular region does not satisfy the system, then nothing else in that region will either. And if a test point in a region does satisfy the system, then everything else in that region will as well, right? To flip, say, over the green inequality, I would need to walk across the green line, or to flip over the black inequality from true to false, I would need to cross over the black line. So either way that you want to go about it, either picking test points or using kind of geometric intuition, if we solve things in terms of y greater than or less than some function of x, then we kind of know whether we want to be above or below that line. But in this case, I see that I want to be above the green line and above the black line. So I'm going to actually shade in this region. So this blue shaded region represents my solution set. Anything in this region, any point that is above or on the green line, and also strictly above the black line, will represent a solution to this original linear system, system of linear inequalities. So we represent these solution sets by graphing because, well, how else am I going to represent a solution like this? Right? It's not going to be very easy, other than just, maybe writing it a little more simply like this or something. The standard way is to represent it with a graph like this. It might be the case also that a point of interest is, say, the intersection of these two lines. That might be a point of interest for us. We might find that. We don't have to find it for the solution, though. But there are some applications and optimization methods and things based off of this idea. And in those methods, it's actually quite important to find these points of intersection. So we could, find the point of intersection of these two lines and label that as well, if we were going to use that in an application, but that's not necessary for the solution here. Okay, let's look at this system of linear inequalities. So here I have x minus 2y less than 3, which I can rewrite as 2y bigger than negative x plus 3, or y bigger than negative 1/2 x plus 3 halves. And I have a second inequality that y is less than or equal to 1. So I write these a little bit nicer. Now I can graph these. Well, the green inequality is very easy. Y less than or equal to 1 is just this horizontal line through y equals 1. I see that it is a non-strict inequality, so points that are on that line can still satisfy the system. So I'll draw it as a solid line. For the black inequality, y bigger than negative 1/2 x plus 3 halves. So 3 halves is, so there's 1/2, 1, and 3 halves. That's my y-intercept. And let me be careful. This is a strict inequality, so I will draw an open circle there. And then what? If I go to x equals 3, then y equals 0. I'll draw an open circle there as well. Went a little further with that dash than I wanted. And then again, because I have a strict inequality, y has to be strictly greater than this. I will draw that line as a dashed line. So points on that line cannot satisfy the system of linear inequalities because they wouldn't satisfy the black inequality. Now I know that y has to be bigger than the black inequality and less than or equal to the green. So I've got to be above the black line and also below the green line. So it looks like my solution set is this kind of bottom right triangle down here. This is where I'm above the black line and below the green line. Points on the green line over here on the right would be solutions to the system of linear inequalities, but points on the black line, the dashed line, would not be. So for instance, 3, 0 would not represent a solution to the system because it doesn't satisfy the black inequality. We would get, what would we get? 0 is strictly greater than 0, which is not true. Any questions so far? Okay, let's look at this one. So we have 3y bigger than x plus 2, or y is bigger than 1/3 x plus 2/3. And then we have negative 2x plus 6y is bigger than 8. So this was our first one. This tells me that 6y is bigger than 2x plus 8, or y is bigger than, well, 2 over 6 is 1/3 x plus
I
8
do have a
over,
quick question.
yeah, sure.
So with the equation right there, like the 3y, how did you get that from that? Did you plug in the equation to the other equation? Because it's kind of, are you kind of moving fast for me, so it's kind of hard for me to catch on. I'm sorry.
Yeah, moving from here to here, I just divided by 3.
Okay, so you're
Yep.
basically solving for y.
Exactly. Yeah, we're just solving for y. That's kind of the first step to make these a little bit simpler to deal with.
Okay, no problem. Thank you. I just missed that step.
Yeah, sure. No, good question. Yeah, so that's all we're doing is we're just to make it, number one, a little easier to graph, to get it in kind of slope intercept form. That can sometimes be helpful. But number two, so that we can get a clear idea of like up here, we were able to see y bigger than meant that we wanted to be above the black line here, and y less than or equal to meant that we wanted to be below the green line. And we can more easily identify the pseudo quadrant that our solution lies in. Yeah, so that's the main reason that we're doing that. If I had something like negative y is bigger than some stuff with x's, then it's like, because it's negative y is bigger than, I'm looking for solutions that are below that line, and it's kind of hard to keep straight. So if I always just isolate the y by itself, just makes it a little bit easier to make sure that I'm getting all of the signs right, the plus and minus sign, and also the inequality sign. Yeah, good question though. And so here we're again solving for y. So I add 2x to the other side, divide by 6. So y is bigger than 2 over 6, they're 1/3. X plus 8 over 6 is 4/3. So now I have these two inequalities. These both happen to be strict inequalities. So my black inequality, if I had y equals 1/3 x plus 2/3, that's going to go through the point 0, 2/3. But again, I want to be careful because it's a strict inequality. I want an open circle there to indicate that that point cannot be a solution to the linear system of inequalities because it's not going to be a solution to that black inequality. So if I go to say x equals -2, that gives me -2/3 plus 2/3 is 0. That's another point on this line. And I want this to be a dashed line, again, because of the strict inequality. So points on this line are not eligible for solving the linear system of linear inequalities.
Sorry, how do you get -2 and 0?
So if we have y equals 1/3 x plus 2/3, if I plug in x equals -2, we get -2/3 plus 2/3 is 0. So when x is -2, y is 0.
Okay.
So this is our black inequality. Again, we use open circles and a dashed line because it's a strict inequality. And then for green, well, we go through what? 0, 4/3. So here is 4/3. That's a 4, not a 9. Again, it's strict, so let me use an open circle there. I see that when x is -4, y is 0. And I actually see that I have two parallel lines. Two parallel lines that are not the same line. I actually have a couple different situations that I could have here. Now, in this case, my black inequality, y is bigger than 1/3 x plus 2/3. I'm looking for values of y that are above this black dashed line. My green inequality, y is, again, bigger than 1/3 x plus 4/3. I'm looking for values of y that are above the green dashed line. So I need to find ordered pairs x comma y that are both strictly above the black dashed line and also strictly above the green dashed line. In fact, in this case, it's just all of the points that are above the green dashed line. So this second equation is more restrictive universally. Sorry, the second inequality is universally more restrictive than the first inequality. Now note that I could have had, let me erase my arrows here. All right, let's hope that this copies correctly. Good. Okay, so for this problem, again, I wanted XY ordered pairs where the Y value was above this line because I have Y greater than, and where the Y value is above this line. And being above the green line means that the ordered pair is automatically above the black line. So that is my region where I'll find solutions. Now, what if I had, let me actually copy this one more time. Okay. What if I had a pretty similar setup? So I have Y being compared to 1/3 X plus 2/3, and Y being compared to 1/3 X plus 4/3. And let me copy this over here, save myself a little bit of writing later on. So what if I had a similar comparison? Whatever inequalities I put here, whether both of them are greater than, like up here, or whether it's mixed, or whether they're both less than, I'm still going to have these dashed lines that represent kind of the boundary lines. But what if instead I had Y less than 1/3 X plus 4/3? My green inequality was Y less than instead of Y greater than, like up here. And my black inequality was Y greater than, like it was before. Well, here I'm looking for ordered pairs that are above the black line, and also, in this case, below the green line. So it's actually kind of this like strip in between the two lines that represents solutions. So in the example above, it was kind of the really only the green line that that really restricted the solutions. The green line was more restrictive than the black line. Every ordered pair that satisfies the green inequality automatically satisfies the black inequality. But down here with one of the inequalities pointing the other direction, well, I have both of them coming into play now. I have to be below the green line, but also above the black line. Now I can copy this down again. As much as I like to make fun of Microsoft all the time, I think they did something to OneNote, and the copying used to be really wonky, and I would be like crossing my fingers hoping that that if I selected and copied or moved something that it wouldn't like blow the whole program up. But it seems to work a lot better these days than it used to. Anyway, that's kind of beside the point. But okay, so if I had something like Y bigger than for the black inequality and Y less than for the green inequality, I end up with a solution set that's between these two lines. I could end up with something kind of similar to up here, but if my inequalities were facing in the same direction, but I had Y less than for both of them, well, now I'm looking for ordered pairs that are below the green line and also below the black line. Well, now it's the green line that's kind of irrelevant, and really the black line is providing the real restriction here. Any ordered pair that satisfies this black inequality automatically satisfies the green inequality. So our solution set is this whole kind of bottom right area. Now, something that's a little strange here is we see that something similar would happen up here, right? If we started flipping inequalities different ways, my solution region, it looks like, is either going to be above or below the green line, and it's either going to be above or below the black line. So in this case, it was below green and above black, and that's what gave me this region. But this region would be like above green and above black, or above green and below black, or below green and below black. So it kind of seems like for each inequality, for each of these lines, to satisfy its inequality, I need to be either above or below. And since I can be above or below on each of two lines, that's 2 times 2, or 4 different possibilities. I had kind of 4 regions here that could satisfy my system of inequalities. I had 4 regions here as well, right? Here's 1, 2, 3, 4, whether I'm above or below each of the black or green lines. But if I look down here, what happened to my 4th region? I kind of have like 1, 2, 3 regions now. My 4th region kind of disappeared. Oh, my 4th region kind of disappeared. I've investigated what happens if I have y bigger than for both, or y less than for both. I've also investigated what happens if I have mixed, where the black inequality is y greater than and the green is y less than. What's my 4th possibility? Well, I guess the 4th possibility is the black inequality is y less than, the green is y greater than. So I'm looking for ordered pairs that are above the green line and also simultaneously below the black line. Are there any such ordered pairs that are above the green line and below the black line when the green line is always starting off above the black line? Actually, no. There's no solution here. There's no ordered pair x comma y that will satisfy this. How can we see that a little more clearly? Well, if I have y minus 1/3 x less than 2/3 and y minus 1/3 x bigger than 4/3, when I choose whatever ordered pair I want, pick a number for x and a number for y, doesn't matter what they are, no matter what you pick, I get some number over here, and I'm demanding that that number simultaneously, that same number, be less than 2/3 and bigger than 4/3. Of course, that's not going to happen. I could demand that that number be less than 4/3 and also less than 2/3, in which case just the restriction forcing that number to be less than 2/3 is all that matters, because if a number is less than 2/3, it's automatically less than 4/3. That's our situation over here. I could demand that that number be bigger than 4/3 and also bigger than 2/3. But again, a number being bigger than 4/3, automatically it's bigger than 2/3. That's our situation here. Or I could demand that a number be between 2/3 and 4/3. That's what we have here. So this feels a lot like a one-dimensional case, like a one-dimensional inequality, where I might have a solution set that looks like an area between 2 numbers. If I have 2 points of interest and I want to be to the left of both of them, I can have, whoops, I don't know how OneNote thought that I wanted to draw that, but I could have a solution set that looks like this. If I want to be to the left of both of these, if I want to be to the right and to the left, I'd get that. If I want to be to the right of both of these numbers, I would get something like that. And then my last case, if I want to be to the left of the left number and to the right of the right number, no solution. So we have this kind of a setup in compound single variable inequalities. And we can have the same kind of setup here, right? So it's this is kind of an edge case, and it kind of mirrors this idea of single variable linear inequalities. Because really what we have, where did I write that? Here. Really what we have is kind of the same number on the left-hand side. This XY coordination is the same in both inequalities. So it just kind of represents one number, just kind of where we're at along kind of that axis. Okay. So this edge case, where I have two parallel lines, we treat a little bit differently. It's a little bit of a special case, still follows the same logic and the same methodology as above, but it just looks a little bit different. Or if I have two lines that intersect one another, then I'm expecting that one of my four kind of pseudo quadrants is going to be the solution set. And then just taking care for each of the boundary lines, whether or not it should be dashed or solid, whether it's a strict inequality, in which case I make it dashed, or a non-strict inequality, make it solid. Any questions so far? All right, and then we're going to set up a system of inequalities here and just evaluate that system at two different points to see whether she makes a profit or not in these different scenarios. So Caitlin sells her drawings at the county fair. She wants to sell at least 60 drawings and has portraits and landscapes. So let's call our variables P and L for portraits and landscapes. She sells her portraits for $15 and landscapes for $10. And she wants to sell a total of at least 60 drawings. So she wants P plus L bigger than or equal to 60. At least means bigger than or equal to 60. If it said she wants to sell more than 60 drawings, this would be a strict greater than. And she needs to sell at least $800 worth of drawings total. So she wants her total revenue to be at least $800, greater than or equal to 800. And that's going to be 15P plus 10L. So here's my system of two equations and two variables. I'll leave it as an exercise to graph because I want to make sure that we get a start on chapter 5. So we'll leave B as an exercise. So go through a similar process as up here. Plot out the lines, figure out what quadrant represents the solutions. And we can look at C, for instance, if she sells 20 portraits and 35 landscapes, did she satisfy her constraints? Did she satisfy this linear system? Is P equals 20, L equals 35 a solution to this system of linear inequalities? But we can see right away it's not, because 20 plus 35 is that bigger than 60. Well, this is 55, certainly not bigger than 60. She did not sell enough paintings. Even if she made enough revenue, she didn't sell enough paintings. Maybe she wants to sell a bunch of paintings because she wants to get her name out there and get marketing and all of that. So she did not satisfy that first inequality. If she sells 50 and 20, if P is 50, and L is 20, does this satisfy the system? Did she sell enough paintings and make enough revenue? Is 50 plus 20 bigger than or equal to 60? Yeah, it is. She sold 70 paintings. She sold enough paintings to satisfy that first restriction that she wants to sell at least 60 total paintings. Did she make enough revenue? So is it true that 15 times 50 plus 10 times 20, is that bigger than or equal to 800? Well, 15 times 50 is like 7.5 times 100, or that's what, 750, plus 200, is that bigger than or equal to 800? Yes, it is. So 950 bigger than or equal to 800. She did make enough revenue as well. She sold enough paintings, she made enough revenue. Yes, this is a solution. This one is not. As an exercise, graph the system and check these 2 points on your graph and make sure that this one is not a member of the solution set and this one is. Any questions so far? Okay, so in the last few minutes here, I want to get a start on chapter 5. We are going to move fairly quickly through chapter 5 because through at least parts of chapter 5. A lot of chapter 5 is a recap of Math 90 material, and that is a prereq for this course. So we're going to move into factoring in a little bit, but we want to make sure that we build up a little bit of momentum, dust off any cobwebs, make sure that we're kind of all squared away with the basics of polynomials before we move into things like factoring and some more advanced material. So if you're feeling weak in this early chapter 5 material, this would be a good time to kind of, step back, review some of that material, maybe break out Khan Academy or Math TV or something, go through some extra practice problems, just drill a little bit of extra material in these sections to make sure you have that really good foundation for when we move into things like factoring. So chapter 5, we're moving into discussions on polynomials and polynomial functions. And first, let's deal with some semantics, some just definitions of words, so that when we say a certain word, we all know what we're talking about. So the first is the idea of the degree of a polynomial. So the degree of a constant is 0. So if I have a polynomial like 3, this is an extremely simple polynomial, kind of a degenerate polynomial. Its degree is 0. The degree of a power function, like x to the n power, is n. So a power function like x to the n, its degree is n. So x squared, its degree is 2, or x to the 5th, degree is 5. Now, what if we start combining these together? A monomial is a polynomial with one term. Terms are things that get added together or subtracted off one another. So monomial was something like 3 or x squared or 7x. These would be 3 different monomials. A binomial, kind of like bicycle like 2 wheels. A binomial has 2 terms. And we haven't really discussed this idea yet, but I think it's a familiar idea. In particular, has 2 unlike terms. We'll talk about like terms in a minute. So if you kind of are digging through your memory recesses trying to remember, wait, what are like terms? We'll talk about that in a second here. I think we're pretty familiar with that, but we'll talk in a minute a little bit more about that. But a binomial has two unlike terms. So something like 3 plus x, or 7 minus 2x, or x squared plus x, something like this. X to the fifth minus x cubed. These would all be examples of binomials. Two monomials added together where we don't have like terms. In other words, we can't simplify anything here. We can't combine these down into a single monomial. I can't do x to the fifth minus x to the third. If I had something like x squared plus 2x squared, I could simplify that to 3x squared. That would really just be a monomial. And then polynomials, poly meaning many. So this is more than two, three or more terms. And again, we think of these as unlike terms. So something like x squared plus 7x minus 1 would be an example of a polynomial. Or x to the fourth minus x cubed plus x squared plus x minus 1, something like that. Another example of a polynomial. The degree of a monomial is either 0 if that monomial is a constant, or it's the power if that monomial is a power function. The degree of a polynomial is the highest degree of any of its terms. So I look at my three terms. This is degree 2, 1, and 0. The degree of the polynomial, highest degree of any of the terms. This is a second degree polynomial because it has an x squared as one of its terms. Similarly over here, for this x to the fourth and so on, we have degrees 4, 3, 2, 1, and 0. The highest degree of any of those monomials, of any of those individual terms, is 4. So the degree of this polynomial will be 4. The degree of this binomial would be 2. This would be 5. This would be 1. Note that x equals x to the first power. And same with this one as well. Okay, so this should be kind of reminding you of some of this terminology and so on. But again, I want to really make the point that we want to be really solid in these foundations. And this does require some dusting off of cobwebs for most folks, even if you just had an 090 in the last semester, and it's been a couple months. Even if you just had it in the summer, it's been a couple months. If you had it in the spring, it's been a few months. So definitely, read ahead a section or two, refamiliarize yourself with these ideas. Make sure you're ready to hit the ground running. We're going to go a little more quickly through chapter 5 because, again, this is going to be some mostly kind of review material that we're looking to review before heading into factoring. All right, that wraps us up for today. I'll stop the recording.